Well, so you've chosen to look at reaction rates, types and rates, eh? Okay, well, it's one of those interesting areas. It's a little bit more complex, a bit more difficult, but still very interesting. Scientists love sort of classifying stuff. So, of course, if you've got a reaction, you must have a different type of reaction, shouldn't you? You've got to have types. So we've got some different things that happen during reactions that we love to talk about. We can talk about things that are composition reactions, so reactions that create something. So in this case, the example there is you've got A plus B, and that creates a new thing called AB. So A and B are your reactants, and AB is a new product. So best explained with an example, isn't it? So on the bottom there, we've got nitrogen gas, which exists in the atmosphere as N2, and hydrogen gas, which exists in the atmosphere as H2, and ammonia gas is NH3. So this is all balanced. We need 6 hydrogen atoms, 3 times 2, plus 2 nitrogen atoms, which are already there, to make the NH3. So 2 times N, 2 N's, 2 N's, 2 times 3, 6 H's, 6 H's, so it's a balanced equation. So for those looking at earlier stage of equations to understand. And we've got a new product. So nitrogen gas and hydrogen gas are quite different elemental compounds as well, or molecules of elements, and they react to form this thing called ammonia. So a completely new product with new characteristics. And of course you can go the other way, so you can have a decomposition. So we could have ammonia, and often it's a matter of putting a current through it in some way, causing the bonds to break, and you've got back to having nitrogen and hydrogen. So AB in this case is our reactant, and through some form, often application of energy, we end up with 2 new products that are different to the original. Excuse me. So it's about breakdown. So decomposition is breaking down, composition is building up. We also have what's known as a displacement reaction, and we have single or double displacement reactions. So in this case here, we've got a single displacement. We've got this product AB again, reactant AB. It reacts with a thing called C, and C displaces or replaces the A. So we end up with a CB plus A. So we've got 2 new outcomes, 2 new products. This happens with silver nitrate and copper. You may have done this in the past in Year 8 possibly, where you've got some silver nitrate in solution and a piece of copper wire coiled up and hanging in the solution. So 2 molecules of silver nitrate. So that's 2 silver atoms, 2 nitrogen atoms, 6 oxygen atoms. React with copper. The copper displaces the silver. So copper and 2 lots of nitrate. And you've got 2 molecules of silver released, and that tends to coat the bit of copper, so it's on the outside. So you notice that nitrate ions don't take any part, so often they're called spectator ions. The molecule's not actually doing anything, it's just having anything done to it, if you like. And you also have what's called a double displacement. So in this case, we've got AB plus CD become AD plus CB, so the A and C have stayed, the B and D have changed position. And this is a classic one I used to, is this one? No, it's not different. There's one I used to do in class with potassium iodide and, what was the other chemical? Lead nitrate. And the lead and potassium change place and it gets yellow solid. So 2 clear liquids you can end up with yellow solid. This is very similar. We've got silver nitrate, we've got sodium chloride, stuff we put on our chips, so sodium and chloride, silver and nitrogen and oxygen. The silver stays still, but it's now connected with the chlorine, so it's now silver chloride, and it becomes a solid and it will precipitate out. The sodium part, sodium here, has joined up with the nitrate, so it's become sodium nitrate, and it's a solution it's sitting in. So a double displacement, we've got 2 things moving, no spectators, everything's on the move. And then there's a few things that affect the rate that a reaction takes place, how fast a reaction takes place. So reactions need energy. They need energy to occur, and often the warmer or the more energy present, the faster they will occur. So temperature is a big thing. If you put it over a Bunsen burner and heat it up, it'll happen faster. Put it in a beaker of ice, it'll happen slower. You look at the concentration of the reactants. So when we're working with acids, you will maybe have noticed they've got a pH value, but you also talk about the molarity of the acid. And so that tells you how much acid's there in water. So if it's more and more concentrated, then molarity is much higher. So we've got a concentrated reactant, and they'll react faster because there's more of it. There's more of it to react with other things. Particle size is really important. So here's a blob of gravel here. It'll react, but it'll react much slower than the silt because that's got a lot more surface area for the amount of volume it contains. And obviously, clay's even faster. It's invisible at this point on this scale. So if they're nice and big and chunky, they'll react, but they'll react slower than something that's been ground up. And so you do that, of course, when you're cooking a lot. You grind up food so that it reacts and creates a new recipe much faster. And we also use things called catalysts, and they're a chemical which causes things to bind together much faster. So that's the other way we can speed things up. So you've got a couple of theory lessons to have a look at. You've got some experiments you could do, particularly around reaction rate. So if you want to do those experiments, let me know as soon as possible. We need to line them up with Mrs. Parry. You're going to sort of learn more about reactions and how we use that idea of reaction types and speeds in our industry, even in our own bodies, in fact, and use that information to address a particular problem or issue. One of the big areas is possibly dealing with pollution and oil spills and things, where understanding displacement and reaction rates can be quite useful. The mining industry uses a lot of chemicals in this way. And you're going to present this back to the rest of the class. You don't have to stand at the front. You can stand at the front and have a chat. Or you can show a video that you've made for yourself, a poster, usual things. And I'll see you in class.